Okay, before 15 days, we have started chapter 4 methodology, preview, and analysis. So, in this chapter, we have studied some part. Let us review that part and start our next lecture. So, in this chapter, we will study OMT as software engineering methodology, the OMT methodology, impact of object oriented approach, overview of analysis, problem statement. Then regarding this, the example is automated trailer machine, that is ATM, then object modeling, dynamic modeling, functional modeling, and adding operations, iterating the analysis. This is the points regarding this chapter, and for this chapter we will use the book Object Oriented Modeling and Design by Rambagh. So Tata McGrath Hill's publications. So in this chapter we will study the object oriented modeling design is a new way of thinking about problems using models organized around real world concepts. The fundamental construct is the object, which combines both data structure and behavior in a single entity. Object oriented models are useful for understanding problems, communicating with applications, experts, modeling enterprises, preparing documentation, and designing programs and databases. This chapter presents an object oriented software development methodology, the object modeling technique, which extends from the analysis through design to implementation. First, an analysis model is built to abstract essential aspects of application domain without regard for eventual implementation. This model contains objects around the application domain, including a description of properties of object and their behavior. Then design decisions are made and details are added to model to describe the optimize the implementation. The application domain objects from the framework of the design model, but they are implemented in terms of computer domain objects. Finally, the design model is implemented in programming language, database, or hardware. We we describe a graphical notation for expressing object-oriented models. Application domain and computer domain object can be modeled, designed, and implemented using the same object-oriented concepts and notations. The same seamless notation is used from analysis to design implementation so that information added in one stage of development need not be lost or translated for the next stage. So generally term object oriented means that organize software as a collection of described objects that incorporate both data structure and behavior are only loosely connected. There is some dispute about exactly what characteristics are required by an object-oriented approach, but they generally include four aspects such as identity, classification, polymorphism, and inheritance. So, what are the characteristics of objects? Identity means data is quantized or sampled into discrete and distinguishable entities called objects. For example, a paragraph in a document. Suppose there is a document, there are number of paragraphs. Out of them, a single paragraph is a particle or part of that document. A window of workstation. These are the examples of objects. Objects can be concrete, such as file in a file system, or conceptual, such as a scheduling policy in multiprocessing operating system. Each object has its own inherent identity. In other words, two objects can distinguish from each other even they have entire attribute values, a same name or size are identical. Next part is polymorphism. Polymorphism is a Greek word. Poly means many, morphism means form. One name, a different forms. That is, same operation may behave differently on different classes. The move operation, this is the example, may behave differently on different classes. An operation is an action or transformation that an object performs or is subject to write, justify, display, and move are the examples of operations. A specific implementation of operation by a certain class called as method. Because an object-oriented operator is polymorphic, it may have more than one method implementing it. Then modeling is a concept, not an implementation. Most of the effort to, to date in the object-oriented community has been focused in programming language issues. The current emphasis in the literature is on implementation rather than analysis and design. Object-oriented programming languages are useful in removing restrictions due to the inflexibility of traditional programming languages. In a sense, however, this emphasis is a step backwards for software engineering by focusing essentially on implementation mechanisms rather than underlying thought process that they support. More object-oriented development is a conceptual process independent of programming language until the final stage. Object-oriented development is a fundamentally new way of thinking, not a programming technique. Its greatest benefit come from helping specifier, developer, and customers express abstract concepts and clearly communicate them to each other. It can serve as medium for specification, analysis, documentation, and interfacing, as well as for programming. Even as a programming tool, it can have various including conventional programming languages and databases, as well as object-oriented languages. So object-oriented methodology, we present a methodology for object-oriented development and graphical notation for representing object-oriented concepts. The methodology consists of building a model of application domain and then adding implementation details to it during the design of system. We call this approach the object modeling technique, and this methodology has following stages such as analysis, system design, object design, and implementation. So we will study in detail first analysis. Analysis, starting from a statement of problem. Whenever you are doing any program, each program have a problem statement, and so that we can analyze that problem. So analysts build a model of a real world situation showing its important properties. The analyst must work with the requester or as per requirement of customer to understand the problem, because the problem statements are rarely complete or incorrect. The analysis model is concise, that is, in short, precise abstraction of what the desired system must do, not how it will be done. And this object in this model should be application domain concepts and not the computer implementation concepts such as data structures. A good model can be understood and criticized by application experts who are not programmers. The analysis model should not contain any implementation decisions. For example, a window class in workstation windowing a system should be described in terms of attributes and operations visible to a user. That is the concept of analysis. Then second step is system design. The system designer makes high level decisions about the overall architecture. During the system design, the target system is organized into subsystems based on both the analysis structure and proposed architecture. The system designer must decide what performance characteristics to optimize, choose the strategy of attacking the problem, and make a tentative resource allocations. For example, the system designer must decide that changes to the workstation screen must be fast and smooth even when windows are moved or erased, and select an appropriate communication protocols and memory buffering strategy. Then third one is object design. The object designer build design model based on the analysis model but containing implementation details. The designer adds details to the design model in accordance with the strategy established during system design. The focus object design is the data structure and algorithm needed to implement each class. The object classes from analysis are still meaningful, but they are augmented with computer domain data structure and algorithm selected to optimize important performance measures. Both the application domain objects and computer domain objects are described using the same object-oriented concepts and notations, although they exist on different conceptual planes. Then fourth one, implementation. Whenever you have decided to do a program regarding any concept, then first you should analyze, then system design, then next part is design. After designing, next part is implementation. First analysis, object design, then system design, then implementation. The object classes and relationships developed during object design are finally translated into a particular programming language, database, or hardware implementation. Programming should be relatively minor and mechanical part of development cycle because all of the hard decisions should be made during design. During implementation, it is important to follow good software engineering practice so that traceability to design is straightforward and so that the implemented system remains flexible and extensible. For example, the window class should be coded in programming language using calls to the underlying graphics on the workstation. So object-oriented concepts can be applied throughout the system development lifecycle from analysis through the design implementation. The same classes can be carried from the stage to stage without a change of notation, although they gain additional implementation details in the latter stages. Although analysis, as per analysis view and the implementation view, window are both correct. They serve different purposes and represent different levels of abstraction. The same object-oriented concepts of identity, classification, polymorphism, and inheritance apply through the entire development cycle. Some classes are not a part of analysis, but they are introduced as a part of design or implementation. For example, in data structure tree, hash tables and linked lists are rarely represented in a real world. They are introduced to support particular algorithm during design. Such data structure objects are used to implement real world objects within a computer and do not derive their properties directly from the real world. There are three models in OMT technology. So in OMT method, methodology uses three kinds of models to describe a system. First one is object model, which describes the objects in the system and their relationships. Second, dynamic model, which describes the interaction among the objects in the system. And third one, the fundamental model describing a data transformation of the system. Each model is applicable during all stages of development and acquire implementation detail as development progress. A complete description of system requires all three models. Whenever you are doing any program, you require the three models: object model, dynamic model, and the functional model. So the object model describes the static structure of objects in a system and their relationships. The object model contains object diagrams. An object diagram is a graph whose nodes are objects. The object model contains object diagram. An object diagram is a graph whose nodes are object classes and whose arcs are relationships among the classes. The dynamic model describes the aspects of system that change over time. The dynamic model is used to specify the, and implement the control aspects of system. The dynamic model contains state diagrams. The state diagram is a graph whose nodes are states and whose arcs are transition between the states caused by the events. And the functional model, the differences from the functional methodology: object oriented development inverts a previous function oriented methodology as exemplified by methodologies. Primary emphasis is placed on specifying and decomposing system functionality. Such an approach might seem the most direct way of implementing a desired goal, but the resulting system can be fragile if the requirement change. The system-based decomposing functionality may require massive restructuring. By contrast, the object-oriented approach focuses first on identifying objects from the application domain, then fitting procedures around them. Although this may seem more indirect, object-oriented software holds up better as a requirement evolve because it is based on the underlying framework of the application domain itself rather than the ad hoc functional requirement of the single problem. Then what is the technique is used for object oriented modeling development? So before that, we clear concept what is a model. A model is an abstraction of something for the purpose of understanding before building it. A model is an abstraction of something for the purpose of understanding it before building it, because a model omits non-essential details. It is easier to manipulate than original entity. Abstraction is a fundamental human capability that permits us to deal with complexity. There are different stakeholders such as engineers, artists, craftsmen. So build models thousands of years to try out designs before executing them. Development of hardware and software system is no exception. To build complex systems, the developer must abstract different views of system, build models using precise notations, verify that the models satisfy the requirements of system, and gradually add detail to transform the models and the implementation. The object-oriented modeling concepts are applied to analysis design. There are three kinds of object-oriented models composing the object modeling technique: the object model, which describes a static structure; the dynamic model, which describes temporal relationship; and the functional model, which describes functional relationship among different values. Designers build many types of models for various purposes before constructing things. Examples include architectural models to show customers, airplane scale models for wind tunnel test, pencil sketches for composition of oil painting, blueprints of machines parts, storyboards of advertisement, and outline of books. Models serves several purposes. So first purpose is testing physical entity before building it. The medieval mason didn't know the modern physics, but they built scale models of Gothic cathedrals to test the forces on the structure. Scale models of airplanes, cars, boats have been tested in wind tunnels and water mass to improve their aerodynamics. Recent advances in computation permit the simulation of many physical structures without having to build physical models. Not only simulation cheaper, but it provides information that is too fleeting or inaccessible to be measured from a physical model. Both physical models and computer models are usually cheaper than building a complete system and add and enables flaws to be corrected early. Then second one is communication with customer. Architects and products designer build models to show their customers mock-ups and demonstration products that imitate some or all external behavior of the system. Then third one is visualization. Storyboards of movies, television shows and advertisements allow the return to see how their ideas flow. Awkward transitions, dangling ends, and unnecessary segments can be modified before detailed writing begins. Artists' sketches allows them to block out their ideas and make changes before committing them to oil or stone. Then fourth one is reduction of complexity, perhaps the main reason for modeling, which incorporates all the previous reasons, is to deal with systems that are too complex to understand directly. The human mind can cope with only limited amount of information at one time. Models reduce complexity by separating out a small number of important things to deal with at a time. Then object modeling technique. We find it is useful to model a system from the three related but different viewpoints, each capturing important aspects of system, but all required for complete description. The object modeling technique is our name for methodology that combines the three view modeling. The object modeling, that is object model, represent a static structural data aspect of system. The dynamic model represent temporal behavior control of a system. Functional model represents the transformational function aspects of a system. A typical software procedure incorporates all three aspects. It uses data structures, that is object model. It sequence operations in time, that is a dynamic model, and it transforms values, that functional model. Each model contains references to entities in other models. For example, operations are attached to objects in object model but more fully expanded in functional model. We will see one by one in detail. First is object model. The object model describes the structure of object in a system, their identity, their relationships to other objects, and their attributes and their operations. The object model provides essential framework into which the dynamic model and functional models can be placed. Changes and transformations are meaningless unless there is something to be changed or transformed. Our goal in constructing the object model is capture those concepts from the real world that are important to an application. In modeling and engineering problem, the object model should contain terms of familiar to engineers. In modeling a business problem, the term from the business. In modeling user interface with terms from the application domain, an analysis model should not contain computer constructs unless the application being modeled is inherently a computer problem, such as a compiler or an operating system. The design model describes how to solve a problem, and many contain computer constructs. The object model is represented graphically with object diagram containing object classes. Classes are arranged into hierarchies sharing common structure and behavior and associated with other classes. Classes define the attribute values carried out by each object instance and the operations which each object performs undergoes. Second one is a dynamic model. The dynamic model describes those aspects of system concerned with time and sequencing of operations, events that mark states that define the context for events and the organization of events in the state. The dynamic model capture control that aspects of a system that describes the operations that occur without regard for what the operations do, what they operate on, or how they are implemented. The dynamic model is represented graphically with a state diagram shows the state and the event sequences permitted in a system for one class of objects. The state diagrams also refers to other models. Actions in the state diagrams correspond to the functions from the functional model. Events in a state diagram become operations in the objects in object model. Then third one is functional model. The functional model describes those aspects of system concerned with transformations of the value, functions, mapping, constraints, and functional dependencies. The functional model captures what a system does without regard for how or when it is done. The functional model is represented with data flow diagrams, which shows the dependencies between values and the computations of output values from the input values of the functions without regard for when or if the functions are executed. Traditional computing concepts such as expression trees are examples of functional models, as are less traditional concepts such as spreadsheets. Functions are invoked as actions in the dynamic model and are shown as operations on objects in the object model. So, what is the relationship among these models? Each model describes one aspect of system but contains references to other models. The object model describes data structure that the dynamic and functional models operate on. Operations in object model correspond to events in the dynamic and functions in the functional model. The dynamic model describes control structure of objects. It shows decisions which depend on object values and which cause the actions that change object values and invoke functions. The functional model describes functions invoked by operations in the object model and actions in the dynamic model. Functions operate on data values specified by the object model. The functional model also shows constraints and show object values. There are occasional ambiguities about which model should contain piece of information. This is a normal because any abstraction is only a rough cut of reality. Something will inevitably straddle the boundaries. Some properties of system may be poorly represented by models. This is also normal because no abstraction can be captured without loading down the model with so many constructs that it becomes a burden, not a help. For those things that a model does not adequately capture, natural language or application specific notation is still a perfectly acceptable tool. So OMT, a software methodology consisting of several phases of development, formulation of the problem through analysis, design, implementation and testing of the software, followed by an operational phase during which maintenance and enhancement is performed. The OMT technology supports the entire software lifecycle. Some software developers prefer a rapid prototyping approach whereby a small portion of the software is initially developed and evaluated through use. The software is gradually made robust through incremental improvements to the specification, design, and implementation. The notation of objects provide a solid basis for specifying, designing, and implementing software in one pass or gradually building software through multiple passes. Object-oriented software development is anchored to real-world objects. Software objects can easily assume additional behavior associated with their real-world counterparts. In contrast, a rapid prototyping is more difficult with function-based software development since a functional breakdown suitable for a prototype may not be suitable for a full implementation. So OMT methodology consists of several phases. We have studied such as analysis, understanding, modeling the application and domain within which it operates. The initial input to the analysis phase is the problem statement which describes the problem to be solved and provide a conceptual overview of proposed system. Subsequent dialogue with customer and real-world background knowledge are traditional inputs to the analysis. The output from the analysis is formal model that captures the three essential aspects of the system such as object model, dynamic model and functional model. The overall architecture of system is determined during the system design. During the During the object design phase, the analysis model is elaborated, refined, and then optimized to produce practical design. During the object design, there is a shift in emphasis from the application concepts toward the computer concepts. First, the basic algorithm. First, the basic algorithms are selected to implement each major function of the system. Based on these algorithms, the structure of object model is then optimized for efficient implementation. The design must also account of concurrency and dynamic control flow as determined during the system design. Then what is the impact of the object oriented approach? Which Impact of object-oriented approach which differs from the traditional software development approaches like process of software development and ultimately the software product itself. Shifting of development efforts into the analysis. The object-oriented approach moves much of the software development and efforts up to the analysis phase of the life cycle. Emphasis on the data structure before the function. Object-oriented approach focuses attention to the data structure instead of the function to be performed. The change of emphasis gives the development process a more stable base and allows the use of single unifying software concept through the process. So, what is the development process? So, because an object-oriented approach defines a set of problem-oriented objects early in the project and continues to use and extend these objects throughout and the development cycle. So, iterative rather than sequential. Although description of OMT is necessarily linear, the actual development process is iterative. So algorithm begins with the problem statement generated by clients and possibly by the developers. Whenever you are doing any program, any project, the analysis starts with the problem statement, and the problem statement generated by the clients or most possibly by the developers. The statement may be incomplete or informal. Analysis make it more precise and exposes ambiguities and inconsistencies. The problem statement should not be taken as immutable, but they should be served as the basis of refining real requirements. The statements in natural language are often ambiguous, incomplete, and inconsistent. The analysis model is a precise, conscious representation of problem that permits answering questions and building a solution. Subsequent design steps refer to the analysis model rather than the original vague problem statement, that is the ambiguity in the problem statement. The analysis model increases the three aspects of objects such as object model, dynamic model, and functional model. This is the overview of analysis process. Whenever you are generating any program or writing any program, you should to analyze, that is generate a request as per the user, as per developer, as per managers. They form the problem statement. Then with the interviews of user, then applying domain knowledge, then real world experiences, and with the help of problem development we can build the modules regarding that the problem statement. And then next step is the analysis, and then next step is a system design, and last step is the implementation. This is the overview of the OMT technology. Let us start with the first statement, that is a problem statement. This is the first step in developing anything, to state the requirements. Whenever you are doing any program, any project, or solving any question, you should know the what is the problem statement regarding that the program, project, or question. What are the basic requirements regarding that the statement? The problem statement should state what is to be done and how it is to be done. The problem statement has two basic questions: what is to be done and how it is to be done. It should be the statement of needs, not a proposal of solution. A user manual for the desired system is a good problem statement. The requester should avoid describing system internals, as these restricts implementation flexibility. A problem statement may have more or less detail. Many problem statements are ambiguous, incomplete, or even inconsistent. So, require statements, that is problem scope, what is needed, application contains, assumptions, performs needs, design and implementation. There is a general approach, algorithms, data structure, architectures, and optimizations. This is the example of automated trailer machine. So there are number of ATMs. They are connected to the central computers. There are number of banks. They are also connected to the central computers. So whenever I want to withdraw money, there are two ways to withdraw money. First, by the cashier, go to the bank at cashier station and withdraw money. And another way, with the help of ATM machine. we can withdraw money. So these two stations are connected to the central computer, either withdraw from bank or either withdraw from the ATM. So the ATM central computer can update your the transactions. This is the overall ATM networks. This is automated teller machine regarding the object model, dynamic model, and the functional model. So the design of software to support computerized banking network, including both human cashiers as well as ATMs, to be shared by consortium of banks. Each bank provides its own computer to maintain its own accounts and process transactions against them. Cashier stations are owned by individual banks and communicate directly with their own banks and computers. Human cashiers enter account and transaction data. ATM machines communicate with the central computer which clears the transaction with appropriate banks. Then object modeling. This is the first step in analyzing the requirements to construct the object model. The object model shows the static data structure of a real world system and organizes it into workable pieces. The object model describes real world object classes and their relationships each other. Information for the object models comes from the problem statement, expert knowledge, and application domain, general knowledge of the real world. So there are 8 steps. They are the object oriented model performing throughout the 8 steps. First is identity of objects and classes. Prepare a data dictionary. Identify associations, including aggregations between objects. Identify attributes of the objects and links. Organize and simplify objects classes using inheritance. Verify that access paths exist for likely queries. Iterate and refine the model. Group classes into the models. This is the structure, ATM structure, object model with attribute. See the figures in short. This is figure ATM object model with attributes. This is the ATM model with a different attributes. So ATM, this is the ATM, then connected with the central computer. Central computer also connected to the bank computer and its own consortium, which contains the bank code, which consists of bank name, and each bank have its own bank computer with station code, with cashier stations, and each bank have a card code, station code, account code, employee code. Each account code have accounts, different types of accounts. In each account there is balance, credit limit, and type of account, and each account have a customer with the name, address, that it is its KYC. Then bank code associate issues with the cash card with pass cash card with some passwords, have some authorities. Then for the ATM card have types of ATM, date and time, amount, whatever. This is entered through the ATM. This is the overall structure of object model with attributes of ATM. Whenever question may be asked for the describe the object model with attributes of ATM, then you should have to draw this figure and explain each and every part in detail. Then second is a dynamic model. The dynamic model shows the time dependent behavior of system and the objects in it. Begins dynamic analysis by looking for events externally visible, stimuli and responses, then summarizes permissible event sequences for each object with a state diagram. The dynamic model is insignificant for purely static data repository such as database. The dynamic model is important for iterative systems. There are 5 steps to perform dynamic model. First is prepare scenario of typical interaction sequence, identifying events between objects, prepare an event trace for each scenario, build a state diagram, match events between objects to verify consistency. This is format of ATM interface. This is front view of the ATM. This is for message to the users. These are the keys. Then this part, third slot for cash slot and receipts. So this is event flow diagram for ATM example. Whenever you want to withdraw money from the ATM, then user insert card to the ATM, then ATM verify the account process transition. So whenever user insert the card to the ATM, that is communicate with ATM communicate with its consortium, then its consortium communicates with bank, verify card with bank. Okay, then after verification done by the bank communicates to the consortium bank transaction about the bank process of transaction. Then consortium communicates with the ATM and asks display on main screen whether the unreadable card message or request password or request type, then amount, then cancelled message, eject card, failure message, dispense. These are messages from ATM to user. This is the event flow diagram for ATM through dynamic model. Then third one is functional modeling. The functional model shows how values are computed without regard for sequencing, decisions, or object structure. The functional model shows which values depend on which other values and the functions that relate them. The data flow diagrams are useful for showing functional dependencies. Functions are expressed in various ways, including natural language, mathematical equations, and pseudocode. So it have five steps for constructing the functional model. First one, identify input output values. Second one, build data flow diagrams showing functional dependencies. Third one, describe functions. Fourth one, identify constraints. Fifth one, specify optimization criteria. So this is the input output values of ATM system. So system have its own boundary, that is system boundary. This arc, dotted arc, indicates that this is a system boundary. Whenever user insert whenever user insert ATM card, that is cash card, which have bank code and card code. So whenever withdraw money, then ATM machine asks transaction of coin, account type, amount, then ATM gives the cash, receipts, and the messages. This is the input output values for ATM system. Then on top level data flow diagram for the ATM. So cash card reads inputs. Okay, whenever user insert a card, type password, transaction kind, amount, account type, whatever, reads input, perform the transaction with amount and remaining balance, then generate outputs with message, cash, and receipts. This is the top level data flow diagram for the ATM. Then last one part of this is adding operation. Our style of object oriented analysis places much less emphasis on defining operations than more traditional programming based object oriented methodologies. The list of potentially useful operations is open ended and it is difficult to know when to stop adding them. So key operations have been summarized in the object model and they are discovered during the following analysis steps. First, operations from object model, operations from event, operations from state actions and activities, operations from functions, shopping list operations, simplifying operations, then iterating the analysis. Most analysis models require more than one pass to complete. Most problem statement contain circularities and most applications cannot be approached in a completely linear way because different parts of the problem interact. To understand a problem with all its implications, you must attack the analysis iteratively, preparing a first approximation to the model and then iterating the analysis as your understanding increases. So refining analysis model, the overall analysis model may show inconsistencies and imbalances within the across model. Iterate the different stages to produce a cleaner and more coherent design. Attempt to refine object definitions to increase sharing and improve structure. And second one, restating the requirements. When the analysis is complete, the model serves as a basis of requirements and defines the scope of future disclosure. Most of the real requirements will be part of the model. Some requirements specify the performance constraints, and these should be stated clearly together with optimization criteria. Then first one is object model. The initial analysis model is likely to contain flaws that must be corrected by later iterations. The entire model need not be constructed uniformly. Some aspects of problem can be analyzed in depth through several iterations, while other aspects are still sketchy. Analysis and design are rarely completed linear. So in object model, there are total 8 points. We'll see one by one. First one is identify objects and classes. Second, prepare a data dictionary. Third one, identify associations between objects. Fourth one, identify attributes of objects and links. Organize and simplify object classes using inheritance. Verify the aspects paths for likely queries. Iterate and refine the model. Group classes into model. So first is identify object classes. The first step in constructing an object model is to identify relevant object classes from the application domain. Objects include physical entities such as houses, employees, and machines, as well as concepts such as trajectories, seating assignments, and payment schedules. All classes must make sense in application domain. Avoid computer implementation constructs such as linked list and subroutines. These are the classes: software, banking network, cashier, ATM, consortiums, bank computer, account transition, cashier station, account data, transition data, central computer, cash card, user, cash, receipt, system, customer, cost, access, security provision, record keeping provisions. These are the different classes. So then communication line and transaction logs. Then there are some bad classes such as vague, attribute, redundant, irrelevant, and implementation. These are five main classes. They are subparts are vague, maybe system, security provision, record keeping provision, or banking network. Then attribute classes maybe consist of account data, receipt, cache, traditional data. Redundant class may be user, irrelevant class may be cost, and implementation such as transaction log, access, software, and communication line. There are also some good classes such as account, ATM, bank, computer bank, that is bank computer, cash card, cashier, cashier station, central computer, consortium, customer, transaction. So these are nearly about 16 classes can be classified into bad classes as well as good classes. So second part is keeping the right class. Now discard unnecessary and incorrect classes according to the following criteria. There are total seven criterias. First is redundant class, second irrelevant class, third value class, fourth attribute, fifth operation, sixth roles, and seventh implementation constructs. So redundant classes may be the user if two classes express the same information and the most descriptive name should be kept. For example, although the customer might describe a person talking, an airline flight and passenger is more descriptive. On the other hand, if the problem concerns con- contracts for a character airline, the customer is also an appropriate word since a contract might involve several passengers. This is the redundant classes. Second, irrelevant classes. Irrelevant classes may be the cost. If a class has little or nothing to do with the problem, then it should be eliminated. This involves judgment because in other context, the class could be important. For example, in a theater ticket reservation system, the occupation of ticket holders are irrelevant, but the occupations of theater personnel may be relevant. Then value classes. There is ambiguity in the classes. Such classes should be system security provision, record keeping provision, banking network. A class should be specific. Some tentative class may have be ill defined boundaries or to be too broad in scope. For example, record keeping provision is vague. The ATM in other application is a part of transaction. In other applications, it might be included in other classes such as stock scales, telephone calls, or machine failures. These are the vague classes. Then attributes. So attributes may be the account data, record, then transaction data, receipt, and the cache. The names that primarily describe individual aspects or objects should be restated as attributes. For example, name, age, weight, address are usually the attributes of a person. If the independent existence of a property is important, then the make it a class, not an attribute. For example, employee's room would be the class. In an application, reassign the room after the reorganization. Then next is operations. If a name describes an operation that is applied to object and not manipulated it its own right, then it should not be a class. For example, a telephone call is a sequence of actions involving a caller and telephone network. If we are simply building a telephones, then call is a part of a dynamic model, not a object model. An operation that has features of its own should be modeled as a class. However, for example, in a billing system for a telephone call, a call would be an important class with attributes such as a date, time, and destination. Then next part is the role. The name of class should be reflect its intrinsic nature and not a role that it plays man association. For example, owner would be a poor name of a class in case of car manufacturers database. What is the list of drivers that added later? What about the persons lease the cars? There are the different. So owner will be the poor name in case of car. The proper class is a person, probably the customer, which assumes various different roles such as owner, driver, or lessee. For example, a person and employee may be different classes in some circumstances and redundant in others. From the viewpoint of company database of the employee, the two may be identical in a government tax database. A person may hold more than one job. So it is important to distinguish a person from employee, and each person can correspond to zero or to more instances of employee information. Then implementation constructs extraneous to the real world should be eliminated from the analysis model. They should be needed later during the design, but not now. For example, CPU, subroutine, process, algorithm, and interrupt and implementation constructs for most applications, although they are legitimate classes for operating system. Data structures such as linked lists, trees, arrays, and tables are almost always implementation constructs. Some tentative operations ATM classes are rarely implementation constructs. Transaction log is simply the set of transitions and its extract a representation in a design issue.
हॅलो सर.
हम्म, बोला.
बास की आता सर अटेंडन्स घ्या 1.5 तास झालं. बास
Okay.
सर.
Last 15 minutes, 10 minutes, 10 to 15
नाही
सर
minutes.
सर
बाकी
माझं
झालं सर
रोज
आता
झालेले उद्या हा
Okay,
टॉपिक शिकवा.
सर
okay,
बाकी
okay. So communication links can be shown associations. Communications lines can be simply physical implementation of such links. So Rekha, up to this we have studied the record keeping the right classes, redundant classes, irrelevant classes, value classes, attributes, operations, rules, and implementation constructs. Then third one is preparing a data dictionary. Isolated words have too many interactions. So prepare a data dictionary for all modeling entities. Write a paragraph precisely describing each object class. Describe the scope of the class within the current problem, including any assumptions or restrictions on its membership or use. The data dictionary also describes associations, attributes, and operations. So, in a bank system or ATM system, so preparing a data dictionary should contain 11 classes such as account, ATM, bank computer, cash, cash card, cashier, cashier station, central computer, consortium, customer, transitions. There are different classes regarding the ATM structure. So we can prepare a data dictionary regarding ATM structure nearly about 11 points. So we'll study the detailed part of preparing data dictionary in next lecture.